In a precipitation reaction, dissolved substances react to form solid products. In my research lab, we do precipitation reactions all the time as a way to purify our products. The difference between reaction types has to do with the characteristics of the reactants and the products. Reactants are the starting material, and the products are what are made. For this reaction, we need to start with two solutions. We're going to use copper sulfate and sodium hydroxide. Copper sulfate is a light blue solution. Its chemical formula is CuSO4. Sodium hydroxide is a clear solution. Its chemical formula is NaOH. If you mix these together, they get cloudy. This is a precipitation reaction. Our two liquids are producing a solid. What's happening at the atomic level, or to be more precise, the ionic level? CuSO4 and 2NaOH forms CuOH2 plus Na2SO4. We'll try out more precipitation reactions later in the unit, but now let's get into another type of reaction. In an acid-base reaction, a hydrogen ion, H+, is transferred from one chemical species to another. This might sound abstract, but you probably run into acid-base reactions pretty often in your everyday life. As the name indicates for this reaction, we need an acid and a base. Real-life examples of acids include lemon juice, vinegar, and battery acid, which is actually sulfuric acid. Examples of bases are most cleaning materials, including hand and body soaps and laundry detergent. We can measure how acidic or basic something is using a scale from 0 to 14 called the pH scale. In this context, an acid is a substance that dissolves in water to yield hydronium ions, H3O+. A base will dissolve in water to yield hydroxide ions, OH-. We can test the pH of liquids in the lab using a pH paper or a meter. With our pH paper, we're going to measure the pH of our acid, in this case, sulfuric acid. The pH paper shows us that the sulfuric acid is between 0 and 1. It's very acidic. For our base, we're using sodium hydroxide. This time, the sodium hydroxide is near 14. It's very basic. Now we're going to mix the two together. We're going to do this using an indicator. The indicator, called thymo blue, doesn't affect the chemical reaction. It just helps give us a visual indication that change is happening. First, we're going to add our acid to a tube. Then we're going to add our indicator. Now, we're going to add our base. Again, the indicator allows us to see a visual reaction that's happening. As we add more base, you can see it's starting to turn blue. Once it's turned blue, we know that the solution is now basic. This reaction, like everyday acid-base reaction, is a neutralization reaction. In a neutralization reaction, the acid and base react to cancel out their effect. An example is when you have an upset stomach. You have a lot of stomach acid. You can take antacid to neutralize the stomach acid. Okay, let's get into the final type of reaction today. Redox reactions are everywhere, from explosions to how you get your energy from a sandwich. In a redox reaction, electrons move from one atom in the reactants to a different one. Redox reactions are used in basic functions of life to include photosynthesis, cellular respiration, and corrosion or rusting. A simple way to visualize a redox reaction is using a lighter. The butane fuel is ignited by a spark and then starts reacting with the oxygen in the air. Electrons are moving from the carbon in the butane fuel to the oxygen in the air. These reactions happen at a speed that we can easily observe, but that's not always the case. Real-life chemical reactions like rust can happen over a long period of time. Many reactions aren't visible, especially to our eyes, but they're happening around us all the time. In my lab, we work at the microscopic level, so we can't usually see the reactions unless we're looking through a microscope.